Okay, so let's continue with bagging. Okay, bagging again is just another ensemble method that we are going to be looking into, a combination of different classifiers, but it works slightly different. So let's look at how does it exactly work. So bagging stands for bootstrap aggregating, and the main idea here is that, we create different bootstrap samples of a training set. So basically, originally we have a training data set, and what we do is that we create different training datasets from that original dataset by sampling with replacement. So imagine that we have initially a dataset with n different samples. What we do is that one by one we take out one sample of the training data, we put it back, okay, and that's one sample that we put in our new dataset. So think of it as having a bag with balls with different numbers. So you take out a ball, look at the number, and say, okay, 9. You put it in your new dataset, but you return it back to the bag. Okay? So we are sampling, but we are returning the sample to the original dataset. That's what sampling with replacement means. So if you take n samples out of a training dataset randomly, you do that n times and you do it with replacement, okay, you can create different training datasets or different bootstrap samples. And then basically each bootstrap sample that you create is used to train a different classifier, okay? In the case of classification, the final label is assigned by majority voting. In the case of regression, it's averaging. Bagging has been shown to work well with different types of classifiers, for example, neural networks or decision trees, and in fact we'll see that random forests take advantage of that. It's an ensemble method that is focused on decision trees. The formal definition of bagging. So bagging, if we look at the training phase and then the classification or the testing phase, okay, those are the two components. For the training phase, we have an ensemble D, okay, that's the ensemble of classifiers. Originally, it doesn't have any classifiers. And L is the number of classifiers that we want to train. So we decide that we want to work with a given number of classifiers. So then we have an iteration loop such that for each classifier, we are going to take a bootstrap sample from the original dataset C, and we're going to build a classifier for that training dataset. Okay, once we have that classifier for that for that bootstrap training dataset, we are going to add that to the list of ensemble classifiers that we have, and our final classifier is going to be D. Okay, so it's exactly what I said before, but put in a more formal setting. Okay, basically, take your training data, divide it, do bootstrap sampling. So basically, take samples with replacement, sample with replacement. That's going to generate n different subsets. And then for each, it's not subset, I keep saying subset, but it's not subset because it has the same number of samples than the original dataset. It's just that it might not have the same samples, but it's exactly the same size as the original dataset, but with different samples. And then basically one classifier is learned per training dataset, and all of them are put together as the final ensemble classifier. For the classification or testing phase, once we have a testing data point, the testing data point is run through each of the individual classifiers. And then basically for a classification setting, the class that has the maximum number of votes is the one chosen as the final label. For regression, it will be an averaging of all the final labels. So in this case, as you can see, there is no weighting over the decision of the classifiers. Because the classifiers are built on different data sets, it wouldn't be fair to weight them because they are working on different data sets. So the final decision is just based on either a voting process where each weak learner has the same strength in their votes, or just averaging. There are other types of sampling variants. So far we have explained bagging when there's sampling with replacement. Okay, that's the approach that we have explained. The new datasets that we generate have exactly the same number of samples as the original dataset. There's also a sub-bagging approach. So basically the T different training datasets that we create have a size smaller than the size of the original dataset. That could be another approach. And another approach would be sampling without replacement. Okay, so we sample meaning that once a data point is in a bootstrap data set, that data point cannot be again in that bootstrap data set, okay, because we do not replace that. And of course, I mean, all these different options are again options as usual. I mean, these are the way the algorithms are executed. So we are running a software package in R that will allow you to run bagging. Basically, these are all things that are done internally by the algorithm, but in the software package, by running the bagging function, you will be able to select what type of sampling you want to do. This is another example on how can bagging be used on decision trees to basically improve the final decision boundaries or the computation of the final classifier. So imagine that we have a data set and that has two features, and this is the way the positive and the negative, or the asterisks and the positive samples, are distributed. That's our training data on the left-hand side. You know, on the right-hand side we have first possible approach to building a classifier that separates the positive samples from the asterisk samples. Obviously, it's not perfect. You know, there are some positive signs with the asterisks, and there are some asterisks on the positive side. But you know, it's quite good. On the left-hand side, we have yet another decision boundary produced by a second tree. So you can, you know, train a different type of tree and basically focus on singling out different types of features. And on the right-hand side, you have another decision boundary produced by yet another tree. Okay. Again, remember that each of those trees are trained on different data sets, created from the original data set. I mean, but you know, if we've done sampling with replacement, they are going to be slightly different. So the trees that you get are going to be slightly different. And so basically, we can repeat this process as many times as we want. In this case, we have repeated it just 3 times. So what you see on the left-hand side is basically the final result of overlaying the 3 classifiers together, the 3 decision trees together, okay? And so if we look at it, it's exactly what you see in the right-hand side. So that's the final classifier that we have, okay? This is just by applying a bagging approach to decision trees, which means that instead of just creating one single decision tree with the samples that we have, we're going to take the training data set, we're going to apply sampling with replacement and generate 3 or 5 or t different training data sets, and use each training data set to build a decision tree. And then, you know, all the decision trees are put together and all of them vote for a final label, or their outputs are averaged if we are talking about regressions. And this is yet another example with exactly the same data set, the same 2 features, but in this case, the baseline classifier that we are using is a neural network, okay, which we will explain in next class. And basically, the neural networks that we generate, in this case, we are generating 10 different neural networks, and the final result is on the right-hand side. And basically, this is just bagging a neural network. So instead of having just one neural network, we take the training data, divide it into different sets of training data, train a neural network on each of them, and basically put all of them together. After seeing those examples, why does bagging work? Okay, the fact is that bagging reduces the variance of the classifiers. Okay, so if you take, you know, the general distribution of the data and the general distribution of the real labels and the general distribution of the labels that your classifier would output, okay, that difference between the two, which is the variance, is reduced by applying bagging. Okay, it's also another way of looking at it. The fact is that each single classifier that we build, each decision tree, each neural network, or whatever we decide to bag, okay, but each single classifier is unstable, or is more unstable than a combination of several of them. Okay, so just one single classifier has a higher variance than an aggregation of smaller classifiers. And so by aggregating different classifiers, we manage to reduce what's the difference between the actual distribution of labels that we have in our problem and the distribution of labels that our classifier outputs. Bagging, it has been reported in the literature that bagging works well for unstable learning algorithms, okay, but for algorithms that are considered stable, okay, does not tend to work really well. Again, remember that what we refer to as unstable are classifiers that have a high variance, okay, so those classifiers that have high variance, bagging appears to reduce the overall variance by combining different classifiers, whereas if the algorithm itself is already quite stable, bagging apparently does not help, but it can worsen things, in fact. So if you think about potential stable algorithms, like for example, k-nearest neighbor is a very stable algorithm. If you try to apply bagging on that, chances are that your final results will be worse than just using one single classifier. As I mentioned before, bagging works really well for decision trees or for neural networks. The reason being that those two are unstable algorithms, okay? And so by applying bagging in general and learning multiple neural networks or multiple decision trees, the results typically improve. Okay, and now let's continue. As I mentioned before, random forests is just, I would say, a very specific way of applying bagging. Okay, so let's look into that. It's just a refinement. So, we are talking about bagging in general. As I was saying before, bagging can be applied to any type of classifier. It's better if they are unstable, like neural networks or decision trees, but in general, bagging, refers to how can we learn one individual classifier for a given training dataset and how the new training datasets are created based on an original training dataset. And so if we focus on, or what random forests do is that they focus on a specific type of classifier, which are decision trees, okay? And it's not only that, but it also has a very special way of manipulating features. Okay, and we'll look into that. It basically uses random vector features to construct the decision trees. And basically at each level of the tree, a random subset of features is chosen. Okay, so what we mean by random vector features is that rather than taking into account all possible features at each level in the tree, only a subset of those are taken into consideration. So what do I mean by this? So I mean, remember how trees are built, so we start with a root node and then we continue, we explore the values that root node can take, we branch it out, we create new nodes, and this node again, we evaluate, what are the branches that it can take and so on, and all this process was based, remember, on information gain. Right? So in this case, what random forests do is that at each tree split, not all features are considered, but rather only a subsample of those features are considered. Okay, so when we are deciding on, which feature should we use now for this specific node in the tree and compute the information gain and so on, rather than considering all possible features, only a subset of those is considered. Okay, it's typically square root of p or log of p. Okay, the number of features that we consider, being p the total number of features that we have in our training dataset. And then basically the way it works is that similarly to bagging, we have an original training data, then we compute different training datasets by using, for example, sampling with replacement. And for each bootstrap sample, what random forest does is that it grows a tree, okay? And it grows a tree in such a way that the decision at each tree split is based only on the m features that we have selected. And then another important feature in random forests is that there's also a computation of the error rate. So the way random forest works is that once we have the training data set, it leaves out a small subset of that training data for that specific tree that we are growing. And that small data set is used to basically evaluate the error rate. Okay, so once we have grown that specific tree with that bootstrap sample, a very small subset of data is used as a validation. So we run that data through the tree and we compute what's the error for those left out samples, and that's what we define as or what Brainman, which is who is the creator of Random Forests, what he defines as out of bag error rate. Okay, the out of bag are basically some samples that we take out from the training data to compute the error, and so this means that when we build a random forest, each tree will also have an out-of-bag error rate. So we will have an approximate measure of how good or bad that tree that we have built is, with respect, obviously, to the training data. So, as I was saying before, random forest is a bagging approach. Okay, so the creation of the training datasets or the bootstrap samples are created equally to the bagging approach. So basically, we have n different samples in our training set, and we sample them with replacement from the original data. Each of the bootstrap samples that we have will have exactly the same size, and each of those is used to grow a different tree. Once we start growing the tree, again with information gain, we will define the features that we consider at each tree split. It's not all the features that we have, but rather a subset of those features, okay? And that's really important. That subset of features is held constant during the whole forest growing, okay? It means that, not the same features have to be explored at each tree split, but the number of features that we explored is constant. When we talk about sampling with replacement, okay, sampling with replacement, as I was saying, means that we basically take one sample out of the original data, okay, and we return it back to the dataset in the sense that when we randomly take another sample, we can randomly take that same sample that we took before, okay. But approximately, by using sampling with replacement, approximately 1/3 of the cases are left out, okay. So when we are computing the out-of-bag data that we use to estimate the error for each tree, okay, the way this works is that for each testing point that we have, we take the out-of-bag data, we get the prediction from each of the trees, and basically that's what we consider the error for each of the trees. Okay, so again, these are two important components. First of all, sampling with replacement is done. Secondly, for the training data, we leave out a subset of samples that we use to compute the error for each training tree, okay? And that error is basically what we use to compute the strength of the tree. If we look at a graphic representation, again, of how random forest works, we have an original data set. We create all the bootstrap samples that we have there. Imagine that we create 500 different bootstrap samples. We will have 500 different trees. What you see there are the representation of different trees. At each split node, we are choosing a subset of random features, random variables. In this case, we say we are trying t different features out of the X that we have. And then once we have built all these trees, basically the final decision is computed using majority voting. So each of those trees is going to output a label, and that label is going to be used for majority voting. Once we have trained the random forest models with the bootstrap samples, we can also compute the out-of-bag error estimates. To do that, we take a small subset from the bootstrap sample. It's called the out-of-bag sample, which is again around 1/3 of the complete bootstrap sample dataset that we are using to train the model. And with that out-of-bag set of samples, we put them down the tree and we count the number of correct predictions that we get for each of the samples. We're going to call that number ROOB. Okay, and basically that number is the one that's going to determine what is the out-of-bag error estimate for the model that we have trained. Okay, we will repeat this process for all the different trees that we have in the random forest, and the average value will be the out-of-bag error estimate. Another relevant feature when we are using random forests is variable importance. So random forest is an ensemble method that allows us to understand what's the importance that different variables have in the prediction. Okay, and that's really important when we are trying to understand how to, for example, eliminate some of the variables that we have to make the model simpler or to make the model train faster. And so, understanding variable importance is key. To model that, we use the same out-of-bag sample data set. And basically what we do is to understand the importance of a given variable, of a given feature, we take all of its values in the out-of-bag data set and we randomly permute them, okay? And then basically take all those samples again down the tree and compute the number of correct predictions, what we're calling our perm, okay? And in order to understand the importance of that variable, if the number of correct predictions after the permutation is a really high value, meaning that we're still predicting really well most of the samples, even though we are permuting that specific variable, then that means that that predictor is really not very important because, we're still doing a lot of correct predictions. So a really high RPM value could mean that the difference between the correct predictions for the our OOB, and or minus the number of correct predictions for the permutation, that difference is going to be a really small value, meaning that the importance of the variable is really small, okay? And so the way we define, or actually within a random forest package, the way the raw importance of a given variable is defined is by computing the difference between the ROOB and the RPerm for all the trees that we have in the random forest. On the other hand, if you take, for example, all of the values for a given predicted variable and randomly permute them, and the number of correct predictions is really small, the RPerm is really small, then that difference is going to have a high value, meaning that the importance of that variable is going to be high. Why? If that importance is high, it's because when we have changed or permuted randomly its values, the number of correct predictions has decreased a lot, meaning that we really cannot get rid of that variable because otherwise the model could be performing poorly. So compared to boosting, random forests are more robust and they are faster to train because, in fact, in boosting, remember that we had all the weighting features. So basically in boosting, we were assigning a weight to each classifier. And also another important thing is that random forests allow us to handle missing data. It's pretty strong with respect to missing data. But on the other hand, as you might have seen, the feature selection is not explicit. So, at every tree split, we are considering m different features, but, they are randomly selected. We only know that m is the same, but not the samples that we are considering. So that's not very obvious. And it's been reported that, it has weaker performance on smaller training data sets.